Okay, so uh, in this video we are going to do something short about bit stuffing. Bit stuffing is basically mostly in low-level stuff. If you have a packet of a packet of data like this, let me just draw like a crude packet here. This can be anything. Can be like a network packet or a CAN bus packet or a USB data packet. Can be an RS-45 data packet, whatever it is. And then inside this packet, you have bits. You have bits here. This is just an arbitrary number of bits. So you, in most protocols, the packets have predefined structure. So they can say that this first bit represents maybe start of frame, might represent start of frame, and then this other bit, maybe 2 bits, might represent something else, maybe the parity bits or whatever. This might represent the data, and then this might represent something else like an acknowledge, like let's say acknowledge bits. And then the last one might represent what? Maybe end of frame. End of frame, right? Now, you realize that for the bit size, for the data, this is data here. For the data, we have 1, 2, 3, 4. We have 4 bits. Okay, 4 bits. And now, if we get 4 bits here, and then somewhere else in the protocol, in the packet, we have 4 bits. Let's say that's right. So this is 1, 1, 1, 1. So this is 1, 2, 3, 4. So 4 bits. So sometimes this consecutive number of ones might be mistaken for a data packet, all right? Or in reverse, if we know that, if let's say we have like a predefined protocol like CAN, let's say CAN bus, mostly used in embedded, ECUs for vehicles and stuff, and industrial settings, and it's very popular. So CAN bus has its own packet structure. So let's say, for example, that for our frame, this is not like the exact frame that CAN bus uses. I'm just demonstrating. So for a frame, let's say we know that the first 4 bytes, if they are 1, this is 1, 2, 3, 4. If they are 1, they represent, let's say, something start, for example. Okay, so 4 ones represent start, right? So so that's that. Now let's say the next thing is, obviously, as I've said, the next bit might be maybe start of frame. This is a start frame. You can say the next bits are data. So say 1, 2, 3, 4. Let's say there are 6 bits. 1, 2, 3, 4, 5, 6. Okay, so you can have 0, 1, 2, 3, 4, 5. This is data. This right here is data. And then the next ones, we can have 1, 2, 3, 4, 5. Remember, this is an arbitrary packet also. doesn't mean anything. I just want to demonstrate what bit stuffing is. So let's have a 0 here, 1, 2, 3, whatever. So you can see now the next 2 bits is something else. Let's say parity. CAN bus does not have parity, but whatever. I'll explain it. Then the next bits are something else. Let's say end of frame. So this idea is end of frame. Okay, now look at this. If we know that the first 4 ones are start, at any other place that we have 4 consecutive bits, the receiver, so you have like the receiving end here, the receiver might misinterpret those 4 consecutive ones as a start signal. So you see this, the next time we have 4 consecutive bits is 1, 2, 3, 4. It's right here. But these ones are in the data. These ones are in the data. This is data. This is in the data packet. But the receiver may interpret these as a start and these are as a start. So what we do, we break the sequence here. So we want to break that sequence. All right. So if you have a consecutive, this is 1, 1, 1, 1, 1. Let's put a 0 here. 1, 2, 3, 4. This is now the data packet. This is this part right here. Actually, it is starting with a 0. So 0. 0, 1, 1, 1, 1, 1. Okay, 1, 2, 3, 4, 5. All right. Ignore this one. So what we want to do is 1, 2, 3, 4. We break the sequence by putting a 0 right here. So we'll have 0, 1, 1, another 1 here. 1, 2, 3, 4. Actually, we should put it here, right at this point. So after the third one, we put a 0, right? So we are right here, and then we have a 1. So put a 1 there, and then the data continues. So this is a 1, 1, 0. So you can see this bit, we have 3 consecutive ones, then a 0. So the receiver will not interpret, they won't see a sequence of 4 consecutive bits that are 1. They'll see just 3 of them. So basically we have broken the sequence inside the data packet part, and this way we help the receiver interpret these bits as they should be interpreted. So whatever we have done here is what is called bit stuffing. So let's see how we implement this in code in C for embedded, obviously. So remember again, one last thing is that the number of bit sequence we check can vary. Can be anything, can be 5 bits, can be 6, can be 7, depending on the protocol itself. Okay. Okay, cool. So what I'll do, I'll create a new file, call it stuff, simple stuff, simple, let's say basic stuff. Okay, basic stuff. All right, so increase the font size a little bit, minimize this guy. Okay, obviously the first thing is we include stdio.h standard library. Then we'll need some predefined number types. Main. Now return 0. So we need a data packet. We need this packet right here. So you can have it as an int data. What's the size of the data? Let's define it right here. Define data size as, let's say, 10 bits. Okay. Remember, we want to stuff the data bits themselves. So data size, we put it right there, is equal to, so we can have whatever sequence we want, 1 0 0. Then let's have a sequence of 5 bits that are 1 1 2 3 4 5. Okay, and the rest can be anything we want. All right, so how many are this? These this is 1 1 2. These are 9 plus 1 10, which is okay, 10. Right, so any stuff we have to put them in different buffer. So stuffed data, call it stuffed data with its own buffer size. Now the buffer size of the stuffed data is different because we are adding extra bits, which means that we need more space. So you can say S data size is 20. Let's double it, 20. So double this. Okay. Now we need two variables, two counting indexes. So int I and int j and int count. Let me call it number of ones. Okay. This will mean how many ones we have. How many ones? All right. Now we want to loop through this data packet, data bits, and check for a consecutive number of bits. So let's define how many bits do we want to stuff after. So define, like right here, we are stuffing it after every 4 bits. So let's try that. Define sequence as 4, right? Now we loop. So here we loop through data bits for I is equal to 0, and then I is less than the length of this, right? And I plus plus. What we do here, we say if data bits are 1, we count it as a valid 1. We say count plus plus. Now we want to copy this guy into the stuffed data buffer. So we want to copy this one here, but now we can't use a I, which is a local loop variable. Let's use j. So we say s data j plus plus. What this will do, it will add. So j starts at 0. J is equal to 0. J starts at 0. It will say j0 is equal to data I, and then it will increment, post increment the j variable. So the first element of S data will staff data will have the first element of data. Otherwise, if data I is not equal to 1, which is a 0, we reset the count, and then we say S data, we put that 0 inside the staffed buffer is equal to data I. Right? Now here we check, have we reached the length that we want to staff? Basically, have we reached the sequence length? Let me call it sequence length, more descriptive. So if count is equal to sequence length, say count, we reset count basically, is equal to 0. Then we staff. So here you staff the bits. Staff. So we start by saying, by inserting a 0 at the next position after the sequence length. All right. So we'll say S data J plus plus is equal to 0. Okay, is equal to 0. So it means that if we have counted the number of, if we have counted 4 bits, we start at 0 after the 4th position. So basically, in this case we are breaking a sequence of how many bits? 5 bits, because this is a sequence length we are counting. If we want to break a sequence of 4 bits, we use 3 here, but we'll compile and run it and see the effect of that. So here we print staffed data. So for let's say int whatever m is equal to 0, m is less than the length of S data length, data size, m plus plus. What we'll say is printf is an integer, so %d space S data m. Okay, let's compile this and see what it gives us. I'll move this to the side, move to top right, and then just increment it, clear this. Okay, so gcc dash o staff, we are compiling staff bits.c. No, we are compiling basic staff, basic dash o basic staff, then basic staff. You can write a makefile for this anyway if you want. Okay, so count and declared first using this function. So right here we say int count is equal to 0. Compile. So it compiled successfully. Let's run it and see. Basic stuff. All right, cool. Now let's compare it with whatever we have. This is 1 0. Our length, remember, is 3. So this is 1 2 3. After 3 bits we staff. So you can see this was a 1, but this is a 0. and then this 1 2 3 stuff, then 1, right, and then another 1 here. Okay, and the data continues that way. There's 1 1 0 1 1 0 1 1 1 1 0 1 1, counting from the behind. Then this is 1 2 3 1 2 3. So we have stuffed it right there, basically breaking the sequence of consecutive of 4 consecutive bits right there. So at the position 1 2 3 4 5 6, position 6, we have inserted a 0. Now if you notice, you can see this, whatever this is because we have the length of 20, but we are only using 10 bits. So we have to stop printing at this point here. How do we do that? We are only printing 1 and zeros, so this doesn't matter really, right? So the good way of doing this, of like implementing this, is checking when we are printing. We check if s data s data k, no, m is equal to 0. All right, or a 1. Again, there are some worst case scenarios for this statement, but for now let's see whether it will work. M is equal to 1. That's the only time we print. Okay, otherwise we break out of the loop. Let's try that. Compile and run. Right, so you see we have got rid of these values. Now if you check, the length of this is 1 2 3 1 2 3 4 5 6 7 8 9 10 11. So 11 because data size is 10, then plus an extra 0 that has been used for stuffing. So that's that. 1 0 1 2 3 1 2 3 stuff, and continue 1 1 0 1 1. Okay, let's try another bit sequence, the last thing. So if you have 1 2 3 4 5, let's try stuffing here, sequence of 4. So what you only need to change is this length, so we change that, compile it, compile and run. Cool. So you see this is 1 2 3 4. After the 4th bit, we break the sequence by inserting a 0. So the original data has 1 2 3 4 5, but we insert a 0 right here. Then we continue 1 0 1 1 1 0 1 1. Right. So again, this code is not optimized, but it shows how to do bit stuffing. You can use strings or character arrays here to do that job, and then you can use a beta check to just print what you need at this point. The other thing you can do is, if you know prior the length of your data size, you can always have like an exact size of array at this point. But otherwise, that is how to do bit stuffing. Okay, so see you next time.